The logistic regression procedure, also known as the limited dependent variable regression. This is used in instances where the dependent variable varies between only two categories, termed dichotomous, such as high or low, or an event occurring or not occurring, or a decision maker choosing to do something or choosing not to do something. Now, with a dichotomous dependent variable, linear regression produces distorted regression estimates because the error terms are not normally distributed. If you think about a dependent variable with only two categories, either the two categories are equally filled, in which case there is no distribution, or the left side is higher than the right side, or the right side is higher than the left side. In none of those three formulations is the data normally distributed. So we can't use ordinary least squares. Instead, we use the maximum likelihood method. But unlike the least squares method of ordinary least squares, there's actually no mathematical proof. So logistic regression is sort of heading into mathematical territory that is less certain. But it is probably the third most widely used statistical technique in the social sciences, which is why we're going to look at it. And plus, it has lots of applications. You can imagine any decision that needs to be modeled, where the decision is yes or no. Logistic regression is the obvious method for trying to explain an outcome. So let's go get our data. So here we're going to get data, and its term is Logit dataset proliferation. So this is actually my master's thesis from a very long time ago. And here we can see the results. You're looking at 88 cases of decision to build or not build a nuclear weapon. So the theory is, the central hypothesis is that that a positive nuclear proliferation decision, that is an explicit decision to seek or acquire an operational nuclear weapons capability, could be explained on the basis of four trichotomous independent variables. So I've got four independent variables with three categories. This is barely permissible. You're not supposed to use dummy variables in a linear regression. And even though a logistic regression is designed to handle a dichotomous dependent variable, it still prefers continuous interval level values for its independent variables. But at the time that I designed this, I'd like to blame my lack of supervision. But more so, I just didn't have the data. So the most I could do was three categories. So this is applied to a number of cases of proliferation. And so the proliferation decision itself, the dependent variable, is either yes or a no, whether a country acquired nuclear weapons or not. And we have four variables. We have security, which goes from 0, no security threat, 1, a territorial threat, and 2, a severe territorial threat. The alliance is valued as 0 for no security alliance, 1 for a covert or limited defensive guarantee, and 2, a defensive treaty. Prestige is coded as 0 for no domestic pressure for local hegemony, 1 for limited demand for local hegemony, and 2, a great domestic pressure for hegemony. And finally, the fourth independent variable is trade, which is valued at 0 for an autarkic economy, 1 which has limited dependence on international trade, and 2 which is heavily dependent on international trade. Now again, a lot of the diagnostic requirements of logistic regression are the same as they are for ordinary least squares. And so what I've done in the notes is I've included each of the steps, even though we're not going to go through all of the steps, because they're basically direct repetitions of what you have in the regression procedure. So the first step is skewness and kurtosis. I mean, we want the independent variables to be as normal as possible in order to reduce the amount of bias we have. The second test is for multicollinearity. We don't want the independent variables having the same common prior cause, so they cause each other. Now, logistic regression is different in two ways. First of all, the threshold is lower. The threshold for logistic regression is 0.5. In other words, no variable can be associated more than 50% with another variable. And for this particular project, this particular model, because the independent variables have 3 categories, we're not going to use Pearson, we're going to use the Spearman coefficient, which is used when we're looking at ordinal data. So let's go ahead and make the analysis. We go to Analyze, Correlate, Bivariate, and here we're going to put in the 4 independent variables: security, alliance, prestige, and trade. And we're going to click here, not on Pearson, but on Spearman. And then we click OK. Now again, we ignore all values except for the correlation coefficient. And you can see, using Spearman's rule, that security, of course, is related perfectly with itself, but it's at 0.496 with alliance, which is pretty close to the 50% threshold. And if we go down, we do have 1 violation, and that's trade and prestige. And in fact, they're inversely related. It seems that as a state becomes more dependent on trade, the prestige demands of the population go down, probably because the more heavily dependent states on trade are more mature economies, and so they have less demand by their domestic populations to assert the country regionally. So what do we do in a case like this? Well, my argument to keep it is that this is driven by theory, and although it's over 50%, it's not egregiously so. It's just 0.631, and so we're not going to have that much damage inflicted on the bias, or rather on the unbiasedness of the model. It's important to remember that theoretical rigor always matters more than mathematical artifacts. So we're going to keep the variable in. So step number 3 is to, of course, exclude data points that are 2 or 3 standard deviations out or more. So that's it. So now we can proceed to the Logit regression. So we go to Analyze, we go to Regression, and we go to Binary Logistic. Okay, we click on that, and here we have a dependent variable, and we're going to put decision into the dependent variable, and we're going to put the 4 independent variables, prestige, alliance, security, and trade, into the covariates, which is another term for the independent variables. We're going to save some values. We're going to save probabilities and group memberships. And in the residuals, we're going to save standardized. And we're going to click continue. And then we're going to go and click on options. And in options, we're going to click in the statistics and plots section. We're going to click on classification plots. And we're going to click on case-wise listing of residuals at 2 standard deviations and more. And we're going to click continue. And that's block 1 of 1. Now I'm going to show you how we used to do it in the old days. We would then do a block 2. In block 2, we're going to leave decision as dependent, and we're going to put null into the independent section. Now why would we do that? If I told you I'm an expert and there's a 50% chance next year that the economy is going to go well and a 50% chance it's going to go bad, you might be impressed with my talent. But actually, I've demonstrated no greater talent than flipping a coin. As an expert, you would expect me to have an added value that's better than flipping a coin. So just by randomly choosing between 2 choices, we could just guess that the choice would go 50% one way or 50% the other. What we want is a model with independent variables that do better than guessing. So what the null is an independent variable where every category is valued at the same number. Okay, so what we're doing is we're neutralizing the impact of the independent variables, and we're asking what prediction can we make based solely on the distribution between the yes and the no in the dependent variable. And once we've calculated this, we're going to compare it to the model with the independent variables. This is a very important step. It's called the improvement step. And I would say 90% of those that use logistic regression forget this step. it's not enough to show that you have a model that works. You have to show the model that works better than random chance, and you have to measure precisely how much better than random chance. And so that's why we put this null value into the calculation. So then we click OK. All right, and here we have the output for the logistic regression. Okay, now in this contemporary version, that calculation is done automatically. You're going to have two iterations. One where we have a null without the independent variables, and a second which will include the independent variables. And so if you go down here to block 0, the beginning block, you're going to see just the immediate decisions in the dependent variable. We have 59 decisions not to build nuclear weapons, 29 to build nuclear weapons, and so we would predict that 67% of the time countries will decide not to build nuclear weapons. And we do that just on the basis of looking at the dependent variable, right? And we would want to do better than that. Here you can see the estimate of the overall model. It's the equivalent of the F statistic, but here they're using a walled statistic, which is generated by SPSS itself. And here you have a significance of 0.002. I have to say that there are many different approaches and applications and interpretations of the logistic regression. The walled statistic is used by SPSS. I have not seen it used outside of SPSS. So you'd have to basically do a lot of research into the particular domain you're in to find out which school of thought is active. Since I've been using SPSS now for almost 30 years, I have an inclination to use the walled statistic, even though some argue that it's actually a fairly liberal measure. But here, regardless, it's significant, which means we can generalize from the model to the population at large. Now, it doesn't mean that we're looking at nuclear weapons in other ages. We could be looking at the proliferation of other things, like airplanes or zeppelins or battleships. Okay, so it doesn't only apply to nuclear weapons. Okay, so here we have the original model. We have here the chi-square. And the chi-square is used to measure the difference in the model with the null hypothesis versus the model with the 4 independent variables. Here we have the model summary. And here we have a classification table. Now here we've improved our ability to predict the outcome. Right? We have observed decisions and we have predicted decisions. And the overall accuracy is 90%. So we can do better than flipping a coin. We can actually predict when a country is going to build or not build a nuclear weapon. Now, I personally don't like this formulation because it actually privileges the decision to not build nuclear weapons, when really we're interested in predicting those cases when nuclear weapons are made. So here, you'll see the decision to build nuclear weapons is correctly predicted 24 times, but it's mispredicted 5 times. That's an improvement of only 82.8%. Well, not an improvement, but rather a success rate of 82.8%. The way that we calculate improvement, so I'm not going to take the 90%. I'm going to go with the 82%. This is a lot more conservative. I mean, it's quite easy for a country to decide not to build nuclear weapons. Many of the times they rather routinely decide we have no money and then nothing is built. So there's nothing profound there. But for a country to build nuclear weapons indicates a major commitment to an incredibly risky foreign policy strategy. So we would subtract from 82.8% the 67% of the original model. And that's going to give us 15.8%. So that's the improvement. By including 4 independent variables, we've improved the distribution of the outcome in the null model, where the independent variable has been neutralized by having 1s everywhere, and we've increased it to 82.8% by including 4 independent variables. Okay, so let's take a look at these 4 independent variables. Okay, the interpretation is very similar to ordinary least squares regression. You've got a B coefficient, including a constant, which is the y-intercept, which is what we're going to use in the prediction equation. We have here a standard error, So the B coefficient divided by the standard error is going to give us a t statistic, which is not represented here, and that's going to give us a value we can then check on the significance test. It's the equivalent of a t-test, and you can actually calculate the t-test here independently, but here the significance test actually refers to the WALD, but the WALD produces similar results to the t-test. And if you look at all of these, we can ignore the constant, they're all below the threshold of 5%. So all of these variables are significant. So not only can we generalize the entire model, because of the chi-square test up here, we can actually generalize each of the independent variables. And we can see that alliance and trade have a negative coefficient, which means they counteract the building of nuclear weapons, and prestige and security have a positive value, which means they're positively associated with the decision to make nuclear weapons. So here we can see that those values are going in the coefficients are going in the correct direction. So I should indicate that the WALD is the equivalent of a chi-square and not R. Right? These are all maximum likelihood estimates, which have a very different logic to them. We're going to see MLEs when we look at some univariate statistics at some later point. You can actually read in the notes. I have a very detailed breakdown of how the how the overall model estimate is made, the chi-square. It's quite complicated, and it's got multiple steps. So I'm not going to go in deeper, except to show you the significance here. Now here we have the observed groups and predicted probabilities. And the way to interpret this chart is you've got a pile of ones and zeros. Each zero represents, as it says down here, 1.2 cases. Right, so it's not one symbol per case. It's sort of attempts to capture all the cases here and then distribute them in terms of a probability. If you're in the extreme left, you have no incentive to build nuclear weapons, so you're going to get a 0. If you're on the extreme right, there's a 100% chance or 100% probability that you're going to choose to build nuclear weapons according to the model. Okay, and if you look here at the center, we've got some dilly-dallying. We've got some zeros and ones around between 0.5 and 0.6. So some countries here choose to build nuclear weapons, some don't, and the model is relatively indeterminate. It means there's a lot of incentives and disincentives to and not to build. It comes out to about equality in terms of the decision. Now, why is this useful? Because it helps show us where there are exceptions. So here around 0.2, we see 2 ones. This actually refers to 2 separate cases. So here we have 2 cases of countries that have chosen to build nuclear weapons, even though they're not under immediate territorial threat, that they have strong allies. And those 2 cases are Israel and North Korea, 2 countries that have a history of not trusting allies because of past exploitation. And so with high levels of insecurity, both countries pursued nuclear weapons. Israel very early on through Shimon Peres, and North Korea tried relentlessly during the Cold War, was blocked by the Soviet Union and China, but then when the Soviet Union collapsed, forged ahead because it didn't want to become dependent on China for its security. Here, around 0.6, we've got Cuba. Cuba probably should build nuclear weapons, even though the Americans have promised not to invade. They, however, are very close to the U.S. And if the U.S. detected a Cuban nuclear weapons program, even though Cuba should build, they probably chose not to build, which is the case here. And finally, we have these 2 zeros off in the extreme end here. Here we have 2 cases of countries that absolutely should have built nuclear weapons. And these 2 countries are actually 4.9 and 4.3 standard deviations above the mean, which is an extreme value. They would normally be excluded as outliers. Who are these 2 countries? Well, they're the UK and France in World War II. The French were the first to deduce the possibility of nuclear weapons. They produced a report, which they sent on to the English, and they hid their fissile material, their uranium, in a cave in Morocco, which was never discovered by the Germans. So the French were very responsible in not losing the secrets of the atom to their German occupiers. The British then received this information, did their own research, and developed the MOD report. And then the British then sent their report on to the US. Both France and England calculated they didn't have the resources to exploit their technology. So they did not pursue a nuclear weapons program, even though they were under dire, extreme threats. France was actually defeated and conquered, and the English were subject to an attack by the Germans during the Battle of Britain. And then for at least a year was vulnerable to being attacked again. So this is the utility of this table here. Okay, you can see here the second model, and here you can see the higher valuations. Here we have this chart here again, and you can see the case-wise list. Here you can see the French and the English being represented here. So this here is the test for the outliers. Now, what we want to do is an overall assessment. Now, the logistic regression coefficient results suggest that it is possible to make reasonable inferences from the sample to the population in the realm of the proliferation phenomenon, and this thus establishes evidence of the external consistency of the theory. Okay, all the variables are significant, so there's no need to exclude any variables. So now we need to conduct some diagnostics that are different than the diagnostics that we conducted with ordinary least squares. And the diagnostic we need to do is the normal distribution of the logistically distributed residuals. So the residuals are normally not normally distributed, but there's a test that can be done to take those and convert them in such a fashion that we can confirm that they're distributed in a way that would look normal if they were normal, right? And that's why we have this chart. So the test that we're going to use is the QQ plot, or the quantile plot, right? And the procedure for this is analyze, descriptive statistics, QQ plot, and here we're going to insert the predicted values, and this is the unstandardized predicted value, and the normalized residuals. So let's open this up so we can see it. Here's the normalized residual, ZRE2. Now it's called ZRE2 because I already saved ZRE1 in an earlier version, so every time you rerun the same value, it's going to enumerate it. But these two values are, in fact, identical. And we click OK. Now, the way to interpret it is we have this line, and we expect this dash of dots to sort of follow it. And believe it or not, this qualifies as sort of following it. Right? If the dots were scattered in such a way that they were not looking like they were in a line, and this line didn't somehow follow this line, then we'd have an issue that we wouldn't have apparently normally distributed residuals, but here we do. Right, so the interpretation is that we can examine the chart. If the points roughly follow the line, then the plot of the predicted and residual values is approximately normal, indicating that the data distribution is amenable to a logistic regression analysis. Uniform divergence from the line, in which all of the data is on one or the other side of the line, indicates that the data is skewed left or right from normal. The greater the distance from the line indicates the incidence of influential outliers. Now we did see we had two outliers, but only two outliers. And in fact, if you're looking at 80-90 cases, 2 cases that are outliers is actually what we would predict. The solution to this is to remove the outliers. In this instance, we have approximate normal distributions, and so there's not much to be done. Now comes the issue of making predictions. This is complex. Now, the problem with logistic regression is we have to go through some arithmetic, and we're going to be using Euler's number, which is 2.718, which you might recognize if you're doing finance, because it's a number that's used to calculate compound anything, in fact, compound interest. So we're going to use Euler's number to try to make a prediction. Okay, so here it's sort of a bit of a complex process. All right, so the equation for the probability of an event, in other words, the probability in this case of making a decision to build a bomb, is going to equal 1 divided by 1 plus Euler's number, which is 2.71, a constant, to the power of minus k, where k is basically the result of the regression equation. So for the ordinary least squares, you had to create a regression equation by using the constant and the coefficients and multiplying them by the values of the variables that you choose for your prediction. Here we're going to do the exact same thing, but then we're going to have to process it through that formula. Okay, so let's go look at our regression equation. K is the regression equation here in red. We've got here minus 1.5541. That, of course, is the constant that we get from the output of the logistic regression. And there we have the 4 independent variables and their coefficients. So let's go ahead and choose some values. Let's imagine that the country has got a security threat that's mild. It has no accompanying alliances. There is domestic pressure for some presence in the region, but the country has autarky. It's valued at 0. So will it make a decision to deploy nuclear weapons, right? That's the question. So we do a very standard calculation. We multiply the coefficients times the values that we chose for the variables. We add then the y-intercept, which is the constant. We get 2.9368. Okay, so now we need to make use of the calculator. All right, so here we have our calculator. Okay, we're going to, it's the PC calculator, sort of standard scientific calculator. And what we're going to insert here is the value 2.9368. So if you recall, this is the value k in this formula here. We're going to convert it to a negative value because, in fact, it is a negative value, right? We have to put a minus on the exponent of k. And next, we need to turn this into the inverse. So we have here e, but what we need it to do is to have the second function because we want this to be an exponent of e. So you'll see down here we have e to the x. If I click e here, we have the ln, which is the natural log, okay, which is actually an application of e as a logarithm. So here we're going to click on the second function, and so this is going to give us e to the minus k. And here you can see x, and x is going to be populated by minus 2.9368. Okay? So there we have it. The value is now 0.053. So that's the number we have here. Okay, so we have to add 1 plus 0.53. And we have it represented here. So it's going to be 1 plus 0.053, and then we have to divide that into 1. All right, and that number is actually going to be 94.9. So in this particular case of the country that we made up, that country has a 94.9% chance of choosing to build nuclear weapons. Okay? Now the probability of an event not occurring can be calculated very easily. It's obviously the opposite of that. So there's a very small probability that the country is going to choose to not build nuclear weapons. So that is the logistic regression.